Hi everyone, I am M. Shivaram Reddy and I am going to present our project that is CrystaLLM, and the main goal of this project is to generate crystal structures using AI. Normally large language models usually used for the tasks like text generation, chatbots. So we want to extend this by exploring whether how we can generate crystal structures using these models. And we know discovering new materials is a very time consuming process. So researchers have to test many combinations before finding a useful material. So by using AI, we are going to speed up this process and so that we can help researchers in finding new materials, new crystal structures in an efficient way. And however, it is not as simple as generating text because crystals must follow physical and chemical properties. So this is the main problem we are trying to solve in this project. So before building the whole system needed for this, we studied the challenges involved in crystal generation. So the first one is symmetry. Every crystal belongs to a specific space group and follows certain symmetric operations. And if these symmetric rules are not followed, the generated crystal structure becomes invalid. And so this is the first challenge. It is the symmetry which if it is not followed the rules, so it is an invalid structure. And the second challenge is thermodynamic stability. If a generated crystal looks correct, even if it looks correct, it may not actually exist in the real world. A physical stable crystal should have a suitable formation energy. So our model should not only generate structures but also considers their stability. And the third challenge is related to CIF files. Crystal structures are stored in CIF format, which contains atomic coordinates with decimal values. These decimal values are very important because even a small change can completely change the whole crystal structure. So because of these challenges, we cannot use these normal general text generation models. So we need some more optimized, more enhanced models for this project. Now let us look at the system architecture. And so as we discussed our challenges before, so to handle these challenges, we designed our system using a microservice architecture. At the front end, we use React and Tailwind CSS to provide a user-friendly interface. Users can enter the required crystal parameters through this interface, and the front end communicates with a Node.js backend. The backend handles routing, authentication, and database operations using MongoDB Atlas, and the AI model runs separately in a Python fast API service. And this service contains our large language model and the physics related components. One important improvement we made is separating the AI model from the main backend. The reason is that running large AI models and physical calculations requires a lot of computational power, and if everything runs in one place in one service, the application may become slow or it can be unstable. So we separated both these so that we can run our application very fast. By separating these components, we improved performance and reduced the chances of system failures. This architecture also makes future scaling easier. Now let us look at the workflow of the system. The user starts by providing input constants. For example, let us take like the user can enter the material composition, target formation energy, space group, and Z value. So these parameters are sent to the generation model, and the model that then it generates the crystal structures in a CAF format. After generation, the CAF file is passed through our visualization pipeline. We use tools such as ASC and NGL view to convert the generated structure into a 3D model, and the user can rotate, zoom, and inspect the structure interactively. This helps researchers analyze the generated crystal and verify whether the structure appears reasonable. So the complete workflow is from user input to AI generation, and finally to a 3D visualization. Now I would like to explain one of our major main contributions. While working with CIF files, we found that standard tokenization methods were not performing well. Most language models use BP tokenization. This method works well for natural language but not for crystal coordinate data. So the problem is that CIF files contain many decimal values and special formatting. When BP tokenization is applied, some spatial information can be lost. As a result, the model spends a lot of time learning the file format itself instead of learning crystal patterns. So to solve this issue, we implemented a byte level tokenizer. In this approach, every character is treated individually. This preserves all coordinates information exactly as it appears in the original CAF file. Because of this, the model can focus more on learning relationships between atoms and crystal structures rather than learning syntax. And this was one of the major contribution in our project. And by this approach, we achieved approximately 56% synthetic validity in generated CAF files. Even if a CAF file is syntactically correct, it still does not guarantee that the material is physically valid. So to solve this problem, we introduced a physics supervision mechanism. We use Monte Carlo tree search, also called as MCTS, together with Align. Align is a graph neural network that predicts formation energy from crystal structures. During generation, it continuously evaluates the structure. If the structure appears unstable, MCTS reduces the score of that generation path and searches for better alternatives. And this process helps guides the model toward more physically realistic structures and instead of that invalid structures. One important difference compared to the base paper is that our approach focuses on thermodynamic stability through formation energy prediction. This increases the chances that generated material could exist in the real world conditions. And the challenges faced during this development. The first challenge was integrating DGL and Align on Windows system. And we encountered DLL errors and compatibility issues during installation. After several experiments, we solved these problems by using compatible versions of PyTorch and related dependencies. The second challenge was model selection. Initially, so explore we, we explored on an autoencoder based approach, but it struggled to handle discrete atomic information effectively. After analyzing the result, we switched to an auto-recursive transformer-based architecture, which was more suitable for sequential crystal generation. And the third was the performance. Running both the language model and graph neural network together created issues and backend slowdowns. So we address this problem by adapting the microservice architecture as we discussed earlier. So these challenges, so we overcome these challenges. So by using suitable approaches. And now let us look at the results we achieved so far in our project. Our language model contains approximately 124 million parameters, and the byte level tokenization strategy helped improve the quality of generated CF files. And we achieved around 56% syntactic validity. And the MCTS and Align framework helps guide the model toward physically stable structures. And the system can generate crystal structures according to user defined constraints such as formation energy, composition, and symmetry information. Although there is still some things we still need to improve, but the current results demonstrate that our approach is working and producing some good outcomes. So to conclude, CrystaLLM is an attempt to our to combine language models with material science. Our project focuses on generating crystal structures while maintaining physical validity. The major contributions of our work include byte level tokenization, physics-guided generation using MCTS and LI, and a scalable microservice architecture. These improvements help. So these improvements help to bridge the gap between AI-based generation and real-world crystallographic requirements. And still, we are trying to improve a lot of things in this project. And so that's all. Thank you.